Okay, we've got a ballistic motion problem in two parts, with two different accelerations, so we're definitely going to have to split it up. If you haven't already tried to work this problem, I suggest you do so before watching the video. I'm going to start with part one, which is the straight line motion of the rocket. This rocket moves in a straight line like this, making an angle of 61 degrees with respect to the horizontal. And I'm not going to split this up into x and y components. I'm just going to follow the motion along the straight line. So for this motion, I just have my 5 quantities here. Now from the problem statement, I don't know how far it goes, but I know that it starts from rest, has an acceleration of 45 meters per second squared for 5 seconds. Alright, so let's go ahead and solve for what we don't know. I have that delta S can be solved. So that's 0. Okay, so that's 562.5 meters. At the same time, I can solve for the final velocity, which I need because that's going to be the initial velocity for part 2. So that's going to be 225 meters per second. Alright, so now let's consider part 2 of the motion, which is the ballistic motion. So this thing is going to start with some initial velocity, v0, making an angle of 61 degrees with respect to the vertical, right? The final velocity from part 1 is equal to the initial velocity for part 2. And this is going to go up a ways, reach maximum height, and then go down and hit the ground. Now, it's going to travel a distance here, delta y and delta x, before it hits the ground. I think it's going to help me to know delta y, so let me come back up here to part 1. Now in part 1 we found that the distance traveled here was 562.5 meters. So that enables me to find delta y1, right? I know that sine 61 is equal to opposite over hypotenuse. So delta y1 is 562.5 times the sine of 61, which is 492 meters. Alright, so it goes 492 meters up. That means in this problem it's going to go 492 meters down before it hits the ground. Okay. Maybe I don't need that, but I do need the 492 to solve for the max height. So I need to find this max height here. So I guess what I'm going to do is I'm just going to consider the part of the motion where the rocket starts at v0 and reaches maximum height. And I'm only going to consider the y component because I don't really need to know the x stuff. So delta y, v0 y, vy, a y, and t. Now, I already established in the first part of this problem that my sign convention is your standard Cartesian sign convention, that up is positive and to the right is positive. So I don't know delta y2. I know v0 y is 225 sine 61, right? Because here's v0, and so v0 y is here. Vy is 0 because it reaches max height, and the acceleration is minus 9.8. Okay, so I can find delta y now. I use the equation that doesn't have t in it. So 196.8 is my initial y velocity. That gives me delta y is equal to 1975.8 meters. And so the total y displacement is equal to y displacement from part 1 plus the y displacement for part 2. That's 492 plus 1975.8, which rounds off to 2,500 meters. So there's the maximum height above ground level for the rocket. Right? It's not just 1975.8, because you got to add that 492 up here. The second part says, at maximum height, what is the magnitude and direction of the rocket's velocity? Well, at max height, the x velocity at max height is just the initial x velocity, which is 225 cosine 61, and that's 110 meters per second. The y component is 0, right? Remember, just to elaborate on this, that when you're in free fall, the x velocity is constant because the x acceleration is 0, right? And at max height, the y component of the velocity is 0, so that's easy. I've got both components of the velocity at maximum height, and that tells me that the velocity is 110 meters per second in the plus x direction.